start off with Jingting Liu from Mullard Space Science Laboratory, UCL. And the title of Jingting's seminar is A Model for the Langmuir Wave Excitation in Magnetic Holes. So Jingting is a PhD student doing plasma physics at Mullard Space Science Laboratory, UCL. Her research focuses on studying instabilities and the various phenomena associated with them. During Jingting's PhD project, she's investigating the interactions between solar wind electrons and electrostatic instabilities. This involves analyzing simulations and data from Solar Orbiter mission to better understand the electrostatic instabilities in the near-Sun solar wind, their energetics, and their impact on the global evolution of the solar wind. So Jingting, if you'd like to share your screen and you can show your slides.
Yes. Okay. So hi everyone, thank you for having me for this seminar. My name is Jingting and I'm a third-year PhD student in plasma group in MSSL. So today my talk is gonna focus on my recent project on understanding the excitation process of Langmuir wave in the magnet. So to start with, what is a magnetic hole? For people that are not very familiar with this concept, magnetic holes are localized regions in space plasmas where the magnetic field strength significantly decreases. So Turner in 1977 first reported this structure in the solar wind, which is a data plot shown on the right-hand side. And researchers have since observed them widely in various space environments, including planetary magnetosheaths, Earth's cast region, and even cometary environments. And magnetic holes are vary in spatial scales, so ranging from a few electron gyroradii to thousands of proton gyroradii. So a key feature of magnetic holes is their ability to influence plasma waves. People have observed many types of waves within those structures, such as Whistler waves and electrocyclotron, harmonic waves, and etc. So those waves are thought to be generated by different instability mechanisms linked to the complex nature of magnetic holes. Okay. So among those waves being observed around magnetic holes, I'm particularly interested in the Langmuir waves. So why? And Langmuir waves can be seen as plasma oscillation driven by electron motions. And the dispersion relation of these waves is shown here. They relate to the electron plasma frequency omega PE and electron thermal speed WE, which directly relate to the number density and the temperature of ambient plasma. Therefore, Langmuir waves plays a very crucial role in energy transfer and wave-particle interactions, since those waves enable efficient energy exchange between electrons and the surrounding plasma. Okay. And so historically, Langmuir waves have been observed primarily associated with type 2 and type 3 radio bursts. However, there's a recent study by Bordeaux in 2023 reveals that Langmuir waves appear very frequently inside magnetic holes than other solar wind regions. So this plot on the left shows a distribution of Langmuir waves throughout the solar orbiter's trajectory observed by the RPW instrument. And the table on the right is the number of events they find using different functions on solar orbiter. So you can see the frequency of different source Langmuir waves are quite different, which are these dots shown in this plot. But what's more interesting is for the table on the right, we can see the Langmuir waves being observed relate to magnetic holes are quite, the amount is quite significant. And actually, in their study, outside the radio burst Langmuir waves, around 8% of solar wind Langmuir waves are actually inside magnetic hole intervals. And it's also worth to notice that our spacecraft, solar orbiter, do not always see magnetic holes. We're only passing through this kind of structure by luck, and actually compare with the total solar orbiter mission life. Until now, the time you can see magnetic holes is actually less than 0.1%. So that kind of tell us that the Langmuir waves must certainly have a strong relationship with this kind of magnetic hole structure. Okay. So last thing before I start explaining our work on these questions, let me very briefly explain how Langmuir waves are triggered. And so these waves are triggered through the classic Fontaine instability, which is when you have a small population of fast electron form bond on the tail of the velocity distribution of electrons in a plasma. So this non-equilibrium distribution creates a positive gradient region in the velocity space and leading to wave growth through the energy transfer from the electrons to the wave. So those overtaking electron will lose their energy to wave to excite the wave, and you can observe them after that. If we look into the dispersion relation again more carefully, you can see the electron plasma frequency omega PE, which has the equation like this, and thermal speed WE is proportional to the number density, which is height of the distribution, and the temperature, which is width of the distribution. So changing those parameters will significantly reshape the distribution functions, and the waves triggering will process will affect the electron distribution, and vice versa. Okay, since we have now know the basic idea of how Langmuir waves are triggered and how it relates to the magnetic hole structures, does it make it easier to happen? So here I draw a very simple ideal magnetic hole structure, which is basically just having a low magnetic field strength region in the middle, and on the both sides you have like higher magnetic field strength region. This is definitely will not be the same in the real life, because in real life it will be much more complex. But this is a simple demonstration of what magnetic holes might look like. Okay, so we have the X0, which is high B field region, and X1 in the middle is the low B field region. And what happens when particles, or electrons in that case, travels through the structure? So we can estimate this motion of electrons in this kind of changing environment through the adiabatic invariant. So here, mu is the first adiabatic invariant, also called the magnetic moment. And the equation is proportional to the perpendicular velocity and the magnetic field strength. So what happens when electrons travel from X0 to X1? When you experience the decreased magnetic field strength, to conserve the adiabatic invariant, vapor should also decrease. However, the total kinetic energy for this particular particle should not change if nothing else happens. So they will then the V parallel component of this particle will increase. And in the distribution function, we shall see like that. So from X0 to X1, you have your distribution function looks like this at the beginning. the electron will start going to this direction, follow the red arrow, according to their energy contour. And it's same for the reverse process from x0, from x1 to x0, which is from the low to high B field region. The electron should all move to higher pitch angle if the magnetic moment is constant. Okay, this plot showing the same thing I just explained. It's energy of electrons, kinetic energy of those electrons are the same, which are at different place in their distribution function. And when B field changes, you will move along the energy contour. Yeah, by the ratio of how B magnetic field is changed. Okay, so this but if we think more carefully, you can see the electron will move together. Means the ratio of all electrons, the V-perp changing ratio of all electrons should be the same, because they experience the same magnetic field strength change. Therefore, it seems doesn't help the bump until instabilities. It doesn't seem will more easily trigger this kind of instability. So what can magnetic holes do in help with Langmuir waves? So if electrons are only being pushed to lower pitch angle, it seems doesn't help. But that is the scenarios we discussed is when the magnetic moment is conserved. What happens if they do not? So let me explain magnetic moment a bit more. So the mu is conserved if B field variation is small compared with the length scale of the dynamic of electrons, so which means if the change is slow in the system, which indicates that motion is not quite periodic. But if the change is slow in the system, we have the adiabatic invariant. By slow, here we mean it's slow compared with the period of motions. So based on this, we can say that for electron, it must fulfill these two conditions, at least here, to conserve mu, to conserve their adiabatic invariant when B is varied. So first, the gyro radius must be smaller than the size of the structure. So when electron gyro into these kind of magnetic hole structures, you want the gyro radius is smaller than the hole size, where RC is the magnetic curvature, and we need to estimate it. And second, the electron must complete several gyrations while crossing the structure over the entire time period tau. So those two conditions basically constrain the size of these magnetic holes, because when you electron travels through this, and basically it's 3D dimension like side of the magnetic holes is constrained by these conditions. So mathematically, those two conditions are written like sure. So after we expand those two equations, we end up with two rather similar conditions that relate to the pitch angle of particles at the specific energy level. So again, those conditions are when electrons conserve mu. So we can see on the right-hand side of both equations, they are very likely to greater than the left-hand side, where left-hand side are just sine and cosine, so they should have a range from -1 to 1. And the right-hand side are easily to be greater than 1. That means for electrons, most of the time, it should conserve their magnetic moment, which makes sense. But when we experience magnetic depression or magnetic holes, this is different. So right-hand side, we have this term, B, which can be very small because you're inside the magnetic holes. To leave the right-hand side significantly smaller, and the right-hand side, it might lead the right-hand side value less than 1. And also for this term, this partial learn B partial T term is how we kind of estimate the magnetic curvature. It can be very big to make also further make the right hand side even smaller. So I'll apply to the structure of the magnetic holes. So if we have a very deep hole, means very low minimum B field strength, which is this term, or very short, meaning changing the magnetic field strength happen very fast, which is this term very big. For those, so if we have those kind of structures, electron at corresponding energy E can make right-hand side, small enough. Therefore, electron at that condition at specific energy can break their magnetic. So here are some cartoons which show different time steps when spacecraft passing through a magnetic hole structure. So this cartoons demonstrate at T0 we have an ordinary bimaxillion with a core and beam structure. And the electron beam group exists as like a shoulder of the core electron population. So when we start moving or when we're passing the magnetic holes, electrons stop getting into the hole. We come to T1. To conserve the magnetic moment, electron being pushed to smaller pitch angle, following their energy contour. I show this little yellow and the blue arrow here. So being pushed to smaller pitch angle region. So dotted lines are the loose cone angle. You can calculate from mu, and between the loose cone angles, those are the trapped electron populations by this structure. And at T2, I just keep pushing down to lower pitch angle. And at T3, where it is almost the bottom of this hole. So this cartoon on the left showing if nothing happens, electron will just be further pushed down to even smaller pitch angle. However, what if our electrons do not conserve mu? If they can break the conditions I listed in 2 pages before, what will happen? So if electron follow the rule, which is the adiabatic environment, will be pushed down. But if it can break the mu, they shall follow their old trajectory, which is still at their old V perp and V parallel. And this will cause here a little bump showing this distribution function. So if those 2 conditions I listed before is broken, certainly it won't broken for all electrons. It will break. Electron at certain energy cannot conserve that. So, for example, this little purple region is where some energy electrons can break their magnetic moment, and you feel it. You form this little bump, and this positive gradient region can trigger lambda wave. So this is what we get according to the theoretical work. So is this really happen in the real life? So we look into the solar orbiter data using several instruments, including RPW, MAG, and instability. So here we display one case we observed in January 2022. So on the left side, we have the magnetic field panel on the top with the electron number density in the blue color. Bottom shows the B field component separately in RTN coordinate. And on the top right is a spectrum, which the light yellow block is the Langmuir wave we observed. This one. Matching with the pitch angle spectrum on the bottom, this one, you can see where the wave being observed exactly. You can see is at the minimum B field strings we have in this event, and these red lines are loose corner angles for this particular event. We're trying to calculate electron for a wide range of energy through the entire time of this event, and we find only for this specific time, where it's at this whole bottom, we can find the solution for electron at 1,200 eV, and there is we observe the Langmuir wave. Let's look into this wave more in detail. We calculate at 1,200 eV is where electron can break their mu, and ideally trigger Langmuir wave. So if we bring this back into the dispersion relation of Langmuir wave, for waves have resonance velocity of 1,200 eV, which is the red line here, we find the approximate frequency of this Langmuir wave is about 19 kilohertz here. This, of course, since observation here we show the E field observations of this specific Langmuir we found, and we find this frequency is very close to what we expect from the from our model. So of course, since the observations might have a range of errors and the estimation of, for example, magnetic curvatures to calculate the condition are also not very precise, so the calculation may have a range of uncertainty. But for this case, we think observations nicely matches with our theoretical expectation. Okay, to sum up, in this study, we're trying to explain why and how Langmuir waves are frequently observed or triggered around magnetic holes. We shows that the magnetic moment mu in certain magnetic hole conditions, either too sharp or too deep, electrons can break their mu conservation. When electrons do not conserve mu anymore, you can reshape the electron distribution function and form a bond to meet the condition of Langmuir instability. And this model is supported by solar orbiter data, which we do find the Langmuir wave expected frequency according to our model. So for the models, this non-conservation of feedback environment might not only affect Langmuir wave, since it might not always necessarily make a bump, but it will definitely always change the dynamic of electrons, and is a potential source of maybe many other events. So I think this work will help us understanding in homogeneous magnetic field better. Yeah. And this is a rather simple structure, but it's already quite complex for our current spacecraft missions and the understanding of physics. So we hope, based on this work, we can look more into other complex inhomogeneous magnetic field problems. Yeah, okay. Thank you very much, and I'm happy to answer any questions.